Have you ever stared at a screen full of code and felt like you were trying to read an alien language? Yeah, you're definitely not alone. But today, we're going to pull back the curtain and show you the one core idea that powers almost all modern software. And we're going to do it with a really simple analogy that's going to make everything just click. So let me ask you this. Imagine you're running a giant car factory. Your job is to build thousands of cars, all different colors, different features, different models. But how on earth do you do that without starting from a blank slate for every single car? I mean, that would be an absolute nightmare, right? So what's the trick? You start with a single master blueprint, and that is the big idea right there. This one document defines everything a car is and everything a car can do. It is the master plan, and it's the secret to understanding how pretty much all modern programming works.
Now, in the coding world, these blueprints have a special name. We call them classes. A class is just a template, a plan, a set of instructions for creating something. It's super important to remember it's not the thing itself, it's the design for the thing.
Okay, this slide right here shows the crucial difference. On the left, you've got the class. That's our blueprint. It lays out the general ideas, like a car will have a brand and a year and potential actions like start the engine. But on the right, you've got the object. That's the actual physical car you can get in and drive. It's a real instance we created from the blueprint, with all the specific details filled in, like the brand is Toyota and the year is 2020. See? One blueprint, endless unique cars. All right, so every good blueprint needs to specify its materials, right? You can't just say, make an engine. You have to describe what it's made of. In programming, we have to do the same thing. We need to specify our raw materials, and we call these specifications data types. You can think of a data type as just a label you slap on a storage box. It tells the computer, hey, listen up. This box right here, it only holds whole numbers. Or this other box is just for text, nothing else. And this is absolutely critical because the computer needs to know what kind of information it's dealing with. So let's connect this back to our car blueprint. The year, 2020, well, that's a whole number, so we'd use an int, which is short for integer. The brand, Toyota, that's just text, so that's a string. The price of some fancy upgrade might be $19.99, so that's a float, a number with a decimal. And something like is four-wheel drive, that would be a bool, which can only ever be true or false. Every piece of information gets the right label. Okay, we've described what our car is, all its parts and materials, but let's be real, a car isn't just a pile of parts. What makes it a car is what it can do. Our blueprint needs instructions for actions, things like starting the engine or hitting the brakes. In the world of programming, these instructions are called functions. So what is a function? It's really just a chunk of code that we give a name to, and it performs one specific task. Think of it like a prepackaged instruction, like start engine. You write out all the little steps for starting an engine one time inside that function. Then whenever you want a car to start, you just call the function by name instead of writing all those steps out again. It's incredibly efficient. But wait a minute, these actions need to be smart, right? For example, the start engine function probably shouldn't work if the car is already running. The car needs to be able to make decisions. And this is where logic comes into play. Logic is basically the brains of our blueprint. The most basic, fundamental piece of logic you'll see everywhere is the if statement. And it's exactly what it sounds like. Just like the slide says, if a certain condition is met, like the fuel is low, then perform a specific action, like turning on the warning light. The computer just checks if the condition is true. If it is, it does the thing. If not, it just skips it and moves on. This simple check is the heart of all decision-making in code. Okay, but what about repetitive stuff? Like, what if we need to check the tire pressure on all four tires? You don't want to write the check tire code 4 separate times, no way. That's what loops are for. A for loop, for example, is perfect for this. It just has 3 parts. First, you set up a counter. Second, you give it a condition to keep it going. And third, you tell it how to increase the counter each time. It's a super clean way to handle anything repetitive. All right, our blueprint is finally complete. It defines the data, it has the actions, and it's got the logic. But it's still just a plan on paper, isn't it? So how do we actually build a car from it? How do we turn that abstract class into a real, tangible object? Well, it's time to fire up the assembly line. The key piece of machinery here is something called the constructor.
Just think of it as the big green start button for the factory assembly line. It's a special function inside our blueprint that has one job and one job only, to take the plan and actually build a new object from it. So when your code says, hey, make me a new car, it's the constructor that gets called to put all the pieces together.
And here we go. This is what our blueprint looks like in some actual code. Now, don't worry about the exact syntax. Just look at the structure. We start by saying class car. That's the name of our blueprint. Inside, we list its properties, a string for the brand, another string for the model, and an int for the year. And look, there's our action, the display info function. It's all just bundled up neatly in one package.
The blueprint is ready. The assembly line is humming. It is finally time to manufacture our very first car. We're about to create a specific instance, a real object that we can actually interact with. And here is the magic. That very first line, car1, that's us telling the program, hey, use that car blueprint and build me one object. We'll call it car1. Then we just use the little dot to access its properties and fill in the blanks. The brand is Toyota, the model is Corolla, and the year is 2020. And for the final step, we call its function, car1.displayInfo, telling our brand new car to do its thing. We just brought our blueprint to life. It's that simple.
So why do we go through all this trouble with blueprints and objects and all this stuff? Why is this one idea so incredibly important to how pretty much all modern software gets built, from your phone's OS to the biggest websites on the planet?
Because this isn't just some clever little trick. It's a totally different way of thinking about how to build complex things. It allows us to manage massive amounts of complexity in a way that's organized, that's scalable, and honestly, that mirrors how we see the real world, as a collection of objects that have properties and can do things. When you get right down to it, this whole blueprint approach gives programmers 3 superpowers. First up is organization. Everything about a car is tucked away neatly inside the car class. Second, reusability. We write the blueprint one time, but we can stamp out thousands, even millions of unique car objects from it. And third, and maybe most importantly, managing complexity. We can build a huge, complex system, like a traffic simulation, by just focusing on one simple, understandable piece at a time, the single car.
Look, the concept of a class as a blueprint isn't just for cars. It could be a blueprint for a user profile on a website, or a bank account, a character in a video game, or a product in an online store. The logic is exactly the same. So, the only real question left is, now that you understand the blueprint, what would you build?